Hello everybody, welcome to day 2 of the 5th annual SSEP National Conference at the Smithsonian's National Air and Space Museum. My name is Jeff Goldstein. I'm the Center Director for the National Center for Earth and Space Science Education, and I'm really excited to start day 2 off with a very special presentation by Dr. Jim Green, who's the Planetary Science Division Director at NASA headquarters.
Thank you very much, Jeff. Today we're going to talk about a historic event. It's coming up. It's in our future. And we're barreling at more than 14 kilometers per second at it. And it's an encounter with the small body, dwarf planet, Pluto. So, some of you in the audience remember Pluto as indeed a planet, others not. But here's the important things to remember. Pluto is so important to understand the origin and evolution of our solar system. NASA does not care what we call it. We need to get there and see what it's all about. And here's the reason why. When we look at our planets, we see terrestrial planets. Those are all close to the sun. So there's Mercury, Venus, Earth, and its moon, and Mars. And it has 2 moons, very small though. Then we have another set of different types of planets. These are called the giant planets: Jupiter, Saturn, Uranus, and Neptune. These are largely gas giants. Some have a lot of molecular hydrogen, some have other ammonias and gases, and we call those ice giants. But those are all huge planets. And then there's a region beyond Neptune that we call the Kuiper belt. And Pluto is one member of that set of objects. In the last 25 years, we've discovered an entirely new part of our solar system, the Kuiper belt. Pluto was found in 1930, the very first object. Right now, it's the largest object in the Kuiper belt, but there's probably tens of thousands of Pluto-like objects beyond the orbit of Pluto, out to about what we call 55 astronomical units. 1 AU, or 1 astronomical unit, is the distance between the sun and the Earth. So 55 astronomical units is a tremendous distance away. So in a matter of days, we're going to be flying into this region, into the Kuiper belt. Now, we have found right now, even though we think there's tens of thousands of Kuiper belt objects, some of them are spherical, some are egg-shaped, some have moons. They're a very diverse set. And many of them are a completely different set of colors, which tell us their composition is quite different. They're similar to the asteroid belt, which is that group of objects that's trying to become a planet that exists between Mars and Jupiter. But indeed, these are a completely different set beyond Pluto, called the Kuiper belt. They are remnants from the beginning of our solar system. And so we want to see what they look like. Now here is some of the first observations from our mission called New Horizons that's speeding towards Pluto. And you can see Pluto, and you can also see one of its 5 moons, and it's called Charon. But what's really interesting about this particular movie is it looks like we haven't registered the frames. It looks like Pluto is dancing back and forth. And it turns out we have Pluto and Charon orbit a barycenter. They do a dance. And the reason for that is Pluto is huge. It's about the size of the United States, and Charon's about half the size of the United States. And they have a significant amount of mass. And the center of mass in those 2 bodies is outside the surface of Pluto. Now this causes tremendous chaos with the with the moons that orbit around the body. Now here we've co-registered Pluto, and Charon then looks like it moves around Pluto, but this is just an artifact so that we can see what this body looks like. Now, when we look at the orbits of all the other 5 satellites, and they are in what we would call a little chaotic. These moons are not what we call tidally locked. They don't have one face. pointing towards the planet all the time. Charon does, but all the others, Nix, Hydra, Kerberos, all spin around, and we believe they're probably oblong, maybe football-shaped. So now we're going to fly through the system. Now the orbit plane for these moons are in the equator of Pluto, but the spin axis of Pluto is laying down, pointing near towards the Earth, which is very different. So this allows us to look at all the moons in their orbits. This is the trajectory. The red line is the trajectory of New Horizons through this system. And as I mentioned, it's moving at a tremendous rate, more than 14 kilometers per second. That's about 30,000 miles an hour. So it's going to go fast. Now, what's really interesting about this system is once we started to look at the moons, and we recognized that these moons do not have a significant amount of gravity, so if there's collisions that occur, then pieces fly apart and the moons don't have enough gravity to bring the material back. And so that means this place may be full of debris. Full of debris. There may be rings around Pluto. There may be other moons that we need to find. And we need to know this because we're flying through this system, and a grain of rice would take the spacecraft out. Just a grain of rice. Now, that means we've invented several trajectories. We call these Shabbats, which means safe haven by other trajectory. We're constantly looking at this environment, constantly trying to find what the hazards are. This mission may be destroyed. This is about $1 billion mission because of a grain of rice-like object that it might hit as it flies through this system. This is the chance we take. It's part of our business. It is a risk that we all have to endure. So let's talk about how we're going to fly through the system. Light travel time is 4.5 hours. So we cannot send up commands and expect the spacecraft in any reasonable way to execute those and then radio back that it has actually executed those commands. That's another 4.5 hours. In 9 to 10 hours, this spacecraft will indeed fly through the Pluto system. So it's on autopilot. On the night of the 13th, it will send its last picture of Pluto, its high-resolution picture of Pluto, back to Earth. And then it's going to fly through the system. I'm going to show you a simulation of what it will do over those 12 hours. As you can see up in the upper right-hand corner is what the imagers are seeing. You'll also see on the main part of the image the object Pluto and its moons and the orientation of the spacecraft. So let's see what it does. So as you can see, it's starting to take images. It will then do a plasma roll. That means it's going to look at all the solar wind that's around it, and then it's going to get busy. It does this in an automated fashion. It turns around with jets, very precise jets that allow it to get in an orientation that it can make these scans and take a look at the bodies that it's going to fly through. And as you can see, Pluto is getting bigger and bigger. And in fact, this flyby occurs so fast that we have to plan it well in advance. We actually don't know exactly where Pluto is. Now, isn't that strange? But when you think about it, Pluto was discovered in 1930. That was 85 years ago. And one orbit of Pluto around the sun is more than 247 years. So we've only seen this object move in part of its orbit. And understanding a full orbit is what it takes to know exactly where this body is at. So we have to constantly look at it, constantly make trajectory changes, and get ready for the encounter. Now here is the latest set of data of Pluto and Charon. This just came down. We've created a mosaic of it. This goes to the end of June. And as you can see, Pluto and Charon are really showing some details. There's dark areas, there's light areas. In fact, when we look at true color, the color of Charon is different than the color of Pluto, which means They may have completely different compositions, and that we also don't understand. So with that, let me stop and answer any questions you might have. Thank you very much.
Do we have any questions?
My name is Nishita Desai. I'm from Somerset, New Jersey. I wanted to find out, so once you get the images from the mission, will you be able to tell what the composition of the planets and the moon?
So, indeed, we'll be able to understand what the composition is of the planet. We have what we call spectrometers on board in addition to imagers. We know Pluto has an atmosphere. We're just learning that it might be fairly extensive, bigger than perhaps what a small body like that could hang on to. That may mean that Pluto might be active, might have a variety of hydrological cycles going on its surface. We're going to be looking for potentially some flat areas that might indicate liquid on its surface. We don't know if that's possible, but all those are in the cards. Those are the kind of things we'll be looking at. Yes?
I have two. First one, since it's making kind of decisions on what to do, is it kind of an AI, artificial intelligence?
That's a good question. So what we do is we program it, just like a computer program will run and execute a variety of things. And we use our best knowledge to be able to do that. We've already now made decisions to stay on the normal trajectory. We believe the system is clean enough that we're going to take the chance of flying between Pluto and the orbit of Charon, right through the middle of that system. And so that means all the sequences of what it looks at, where and when, are all uploaded and programmed right now. And it'll run on autopilot. But it doesn't make its own decision.
Second one, you were talking about maybe finding more than 5 satellites and calling them moons. And I've also heard for Earth that sometimes people refer to us as having over 1,000 moons. And I just want to hear your opinion. Like, how many moons do we actually have?
We have one moon. It's called the moon. Okay? It's where we landed on in '69 through the early '70s. And we brought back lunar material and we've analyzed it, and it's just been an enormous boon to our understanding of the solar system. Now, however, we have many thousands of satellites, but these are artificial satellites. These are what we build, put in space, that do indeed orbit the Earth. But the moon was there first. That's our natural satellite. As I mentioned, Mars has 2, Phobos and Deimos, very small, but Pluto has 5.
Hi, my name is Charity Trojanowski from Damien High School in Laverne, California. My question is, what is the plan after it does its flyby of Pluto? Is there an extended study once it goes past there?
So we've used the Hubble Space Telescope, our most powerful space telescope, and also the most powerful ground-based telescopes to look beyond Pluto. And indeed, there's 2 objects in the Kuiper belt that are Pluto-like objects. They're much smaller that the spacecraft could reach. So right now, everybody is concentrating on the primary mission. But by August and September, we're going to be making a decision on what target the trajectory to, and then we'll make a small course maneuver, and then in about 2019, we'll be flying by one of those.
Will it continue on after that even?
Yes. So New Horizons is on a trajectory to leave our solar system and go out into the galaxy. Yes, sir.
My name is Tim Muller, and I'm from Northern California.
Yes, Tim.
How much is the program costing? And how do you answer to the question, is it worth it?
Yeah, so we spent a little more than $750 million on this particular mission. It's important to understand that nearly every bit of that money was spent right here on Earth. It is used to challenge our people. The most talented engineers NASA's ever seen has been on this mission. We've got the top scientists in the world, and so that's great, but why is that important? we believe the Kuiper belt, which has a significant amount of water, was rearranged early on in our solar system, and a lot of water was brought from the Kuiper belt into the inner part of our solar system. And perhaps as much as 60 to 80% of the water on this Earth came from material in the outer reaches of our solar system and was brought to the Earth about 800 million years after we were put together. That is a brand new set of information and gives us a completely different perspective on how solar systems are put together, and in particular, how we use that knowledge to look for other planets around other stars where there potentially is other life.
You handled that very well.
I'm head of planetary science. Thank you very much.